Hey guys, welcome back to our final online instructional lesson for this year, for the 2019-2020 school year. So this will be the last presentation of new content as we are finishing up our unit on probability and statistics. We are going to go ahead and complete the PS.3 notes today, which talks about probability and the normal distribution curve. So if you are available or have the option of printing, you can find the notes on Google Classroom. You can print those off and follow along. Otherwise, go ahead and make sure you take good detailed notes on a separate sheet of paper so that you have these notes available to you to use when we take our assessment. Some of the things that we are going to talk about here in this target are mostly review, or a good portion of going to be something you're familiar with from Algebra 1. And then we are going to branch into some new information. So the first thing that we're going to take a look at is population parameters. Things that, statistical measures that start to segment an entire population. So let's go ahead and jump straight into an example. In problem number 1, it says 18 students in Mr. Gaines' pre-calculus class took a quiz with the following results in ascending order. So I went ahead and placed those from lowest score to highest score. Use your calculator to determine the mean, the median, and the quartiles for this data set. Then construct a simple box and whiskers or box plot for this data set. This is something that you probably did in Algebra 1. You found mean, median, and mode. So let's review those definitions or terms, the statistical measures. Remember, the mean is what we consider often the average of the scores. So you take the sum of the scores and you divide by the number of scores. The median would be the data point or the value that is directly in between the highest and the lowest values of scores. Then the mode would be the value or number, or the score in this case, that repeats over and over. Mode in this example is actually not touched on. We just need mean and median, and then quartiles. Quartiles you probably talked about in Algebra 1 as well. Quartiles are a segment of the data where 25% of the scores lie, where 50% of the scores lie, which is the median, and then where 75% of the scores lie, which would be the upper third quartile, and then what would be above those percentages. So you probably came up with these statistical measures by hand in Algebra 1. We're going to use the calculator to do that here in Algebra 2. So to find the mean, the median, and the quartiles, we're going to use the stat key. So what we want to do here is hit stat, and then our first option is going to be edit. We want to type in each one of these numbers from the list. It does not necessarily have to be in ascending order, but it is in this case. Didn't want to make you watch me type in all of those numbers. So I now have those input into the calculator. Make sure that you do input all of these numbers in exactly as they're shown. So if you make a mistake, everything else is going to be off. So you have to make sure it's worth double checking, going back through to make sure you have all 18 numbers entered exactly correctly. Once you do, we can hit second and then the mode button, which is to quit. Now, we can use the calculator to come up with the mean, median, mode, and the quartiles for this data set, and some other calculations. To do that, you're going to hit the statistics key again, and then go over to the second option in the menu, calculate. The first option underneath the calculate menu is one variable statistics. We're going to select one variable statistics, and then hit enter. This lists a lot of the, let me back up real quick. If you have a newer calculator, when you hit one variable statistics, something you don't have to worry about on the other one, it's going to have list. Make sure your list is what you just put your numbers under. So if you put your numbers under L1, your list should say L1, and it should be automatically set there. Frequency list, we don't need to worry about, and then go ahead and down and hit calculate if you have a newer calculator. And then you should see the screen. So what we have here is all of the single variable statistics that are going to be incorporated in this lesson. The first thing that we needed to find was mean. Mean is represented by a couple of different variables, but one of those is x bar, what we call x bar. So X bar is the first one on the list. So the mean here is going to be X bar, which is, we'll go ahead and round to 2 decimals, approximately 83.72. So the mean or average score is approximately 83.72. Median, if we scroll down, we will find median just listed as MED for the median. And this median value is going to be 84.5. We also wanted to find the quartiles for this data set. So the first quartile would be 75, and that's represented as Q1. And the third quartile for this data set would be 93. This is all of the information that you need to make a box and whiskers plot. So if you remember back to Algebra 1, a box and whiskers plot goes on a number line like I have here. On this number line, we want to make sure that we represent all of this information. So we create a box to cover the quartiles, the quartile 1, quartile 3, and the median. So I have 5 increments from 70 to 85, so 73 is going to lie right in between the first and second increment there, and it's going to go all the way up to 93. Sorry, that's a 75, not a 73, so let me fix that location. Should be in between the, oops, it should be in between the second and third increment there. And then it's going to go all the way up to 93. And so this is my box. In that box, I need to mark the median. So at 84.5, roughly this location, we mark that median. And then we extend the whiskers to the highest score and the lowest score here. So this gives us a visual representation of some of the data. We can see that the first quartile is here at 75, which means 25% of the scores were less than 75. We can see the third quartile here is 93. That means 25% of the scores were above 93. The median here is at 84.5, so 25% of the scores lie in between the median and the quartile 3, and 25% in between the median and quartile 1. The whiskers extend again to the highest and the lowest score. So what we can see is we had some, we can see by this whisker extending a much further, we had some scores that were pretty far off of the quartiles and the means as being lower scores, and then as higher scores were pretty close to the quartiles and means. In part B, it asks us to find the interquartile range of this data. So the interquartile range is the amount of data points that exist between quartile 1 and quartile 3. So I'm going to abbreviate this as IQR. So IQR, to find the interquartile range, we can take quartile 3 minus quartile 1, which would be 93 minus 75, which is 18. So there are 18 points, 18 score values that exist between the first quartile marker and the third quartile marker. Now, one of the things that we would ideally see here is 50% of the data would lie in between those two values. And so if we check this, if we have perfect data, perfectly distributed data, 50% of our scores would lie within this interquartile range. If I go ahead and take a look at my scores, this is where quartile 1 would be cut off. So here, all the way up to quartile 3 would be cut off there. So 8 out of my 18 scores lie within this interquartile range. This question didn't ask us exactly how to find this, but we can find that 44.44, approximately 44.44% of scores lie within this interquartile range. So it's a decent distribution of data based on this information, but not great. Another thing that we can find is what we call standard deviation. And this may be a new term to you, so I have a definition up here on the screen. So standard deviation is the average distance that a point or every point lies from the mean. So our distance between the lowest point and the mean, so 80, the distance between 56 and x bar, and the distance between 100 and x bar, and then 68 and x bar, and the other 100 and x bar, and so on and so forth. If we take the average or the mean of those numbers, we find those distance first, and then take the mean of those numbers, then we have what we call the standard deviation. Now we could find that by hand, but we can save that for statistics if you're going to go there. We will use the calculator for that. We represent this data in terms of a symbol as sigma. So this is a lowercase sigma. We saw a capital sigma earlier this year, which meant to add terms together. This lowercase sigma means standard deviation. So typically you see that represented with a subscript. So in this case, standard deviation, or a sigma subscript x, is the standard deviation. So if I go back to my calculator, I can find that value. And so that value, we'll go ahead and round this to 4 decimals for right now, is 11.7085, approximately. So what this means is that on average, the scores are 11.7085 points away from the mean of approximately 83.72. So what we can see with this value here is that there's a pretty wide spread. This is the average distance. So on average, one standard deviation above the mean would be approximately 11.7. Let's go ahead and round this to 2 decimals. 11.71 units above 83.72, and one standard deviation below the mean would be 11.71 units below 83.72. And so that's the average distance from the mean. Now, we use standard deviation to help us interpret whether data is going to be good fitting or not. So, I got a typo here. Let's change this to D instead of C, and let's change this to D and E. When we start to look at a normal distribution curve, which is where we're headed here, and strong data correlations, we want to find how many scores are within, in cases, 1 standard deviation from the mean or 2 standard deviations from the mean. So basically what we want to find is, for D, we want to find the percent of scores within 1 standard deviation of the mean. So we would take x bar and add and subtract the standard deviation. Take the mean and add and subtract this value. That's the standard deviation. So what this gives us is an upper bound, essentially, and a lower bound. So if I do this, I'm going to get 2 numbers, and I can go ahead and do this in my calculator. So let's clear that out. And let me go ahead and pull in our mean number, which we rounded. Let's use this rounded number for right now, 83.72, and then add 11.71. So the upper bound for this is the value 95.43. I'll go ahead and write this out in words. So let's say this is between 95.43. So this is adding 1 standard deviation, adding 11.71 to the mean. And we can also subtract to find out how far it is the other way, 83.72 minus 11.71, and that would be 72.01. So it says find the percent of scores within 1 standard deviation of the mean. So how many scores lie within these numbers, 95.43 and 72.01? So 72.01 would be on this side of 72. And 95.43 would be on this side of 95. And so we can count there, and we can see that 11 of the scores lie within 1 standard deviation of the mean. So 11 out of the 18 here, and then we can go ahead and find this percentage in the calculator. Approximately 61.11% lie within 1 standard deviation of the mean. We can do the same thing in E and figure out how many or what percent lie within 2 standard deviations of the mean. So now we're going to take x bar, the mean, and we're going to add and subtract double the standard deviation. So then we are going to be looking for scores that are between two values again. In this case, I'm going to take the 83.72, the mean, and then I'm going to add 2 times 11.71. I'm doubling the standard deviation. So that's going to be between 107.14 and another number. So this would be 107.14 would be two standard deviations above the mean, and 83.72 minus 2 times 11.71. Two standard deviations below the mean would be 60.3. So we're looking for scores that are between 60.3 and 107.14. So 107.14 would get everything above the mean. 60.13 would get everything but one score at 56. So 17 out of 18. And if we typed that into the calculator, we would come up with approximately 94.44% of these scores are within two standard deviations of the mean. So these are numbers that kind of give us some information about the spread of the data away from the mean, and eventually will start to lead us into considering if data is what we call a good distribution or not. Now, there are some other things that can create parameters on populations. So in problem number 2, we have a questionnaire that went home to all juniors concerning their ability to bring and use mobile devices at a large school. The questionnaire constituted a census since all of the juniors were surveyed. Excuse me, of the 742 juniors, 564 of them reported having web-enabled mobile devices. What was the population portion for web-enabled mobile devices? Basically what we have here, if we're talking about population portion, we're looking for a percentage of the population that meets a certain criteria. Basically what we can do is we can think of this as a probability. So let's make web-enabled devices an event. Then the number of elements in the event, or the number of people that meet that event, over the number of people or elements in the sample, allow us to find the population portion that have web-enabled devices. So 564 of the juniors say they did out of 742, and then we can go ahead and divide this to figure out that approximately 61.01% of the population is represented as being able to use web-enabled devices, mobile devices. So basically this is a probability, is the same concept as a probability equation. Let's go ahead and take a look at problem number 3. Problem 3 is the same idea but changes what we're looking for here. It says the proportion of eggs that get cracked in a local egg handling facility is 0.023 or 2.3%. If 2,500 dozen eggs are packaged in a factory every day, how many eggs can be expected to crack each day? So in this case, it gives us the population portion that is going to be cracked. So the population portion that is going to be cracked is 0.023. We know that 2,500 dozen eggs, so basically what we can do here is take 2,500 times 12, and that is 30,000. 30,000 total eggs are packaged every day in the factory. What we want to figure out is how many eggs can be expected to be cracked. We don't know that. That would be the number of events in the elements in the event, so we can represent this with an x. So if we multiply 30,000 by 0.023 to get rid of the denominator, we'd find that x is 690 eggs would be cracked every day. So a population portion is basically trying to find a percentage which we can use the ideas of probability that we established in the last target to go ahead and find the portion of population that meets certain criteria. Now, what all of this leads into is essentially what we call normal distribution. So what we find, and you may have seen something that looks like this before in a data set of some kind. This is what we call a bell curve. Maybe you've heard the term bell curve. Your parents would be much more familiar with the term bell curve, which is likely. A bell curve is what we use to represent a wide variety of data. Normal distribution or normally distributed data is perfect to this curve. So what this curve does is it has a mean value. The mean value for this curve is also the median, and it's also the mode. The mean, median, and mode is the exact center of this curve. So when people talk about, when you hear teachers mention grading on a curve, they're basically what they're doing is making all data fit this trend. This is a common trend that represents many things that we see in statistical analysis. So the middle line here is the mean, median, and mode. The most points of data will fit right here on this line. Now, as we start to move left and to the right of this line, data starts to get sectioned up. And you'll see numbers down here on this bottom axis. These are standard deviation numbers. So basically what we have here is, if I take two sections, this is one standard deviation from the mean. So this right here would be represented by x bar plus sigma sub x. The standard deviation, one standard deviation from the mean, would be all of this data. We could do the same concept and go a little bit further and go 4 lines over. This would be 2 standard deviations from the mean. Now, these percentages are roughly estimated, but for data that is normally distributed, it fits this perfect curve here. The majority of scores are going to be towards the middle, and as we start to branch out to the left and to the right away from the mean or the average, we have less and less scores until we get to an unmeasurable amount. So in problem number 4, it says find a population that is normally distributed, or sorry, for a population that is normally distributed, find the percentage of population that lies A within one standard of deviation of the mean. So again, one standard of deviation of the mean would be starting here at 0 and going to the left 1, but also going, sorry, to the right 1, but also going to the left 1. So basically what we'd be looking for is all the percentage that lies in this shaded region right here. So one standard deviation from the mean would mean we're going up one standard deviation. We're also going down one standard deviation. So what I would get here is I would add in, I'm going to get rid of some of that, but I would add in all of these percentage values. So 15 plus 19.1 plus 19.1 plus 15. This would be approximately 68.2%. So when data is normally distributed, or fits a perfect bell curve, if you will, 68.2% of the data is within one standard deviation of the mean. To get 2 standard deviations of the mean, we take the same concept. I'm going to start here at 0. I'm going to go 2 standard deviations to the right, and I'm also going to go 2 standard deviations to the left. Now, notice that all of the numbers are exactly the same to the left and to the right. So what I could also do here is just take the numbers to the right, so 19.1 plus 15 plus 9.2 plus 4.4, and these are all representing percentages, and multiply that by 2, double it. So that would account for also the 19, the 0.1, the 15, the 9.2, and the 4.4 to the left. So if you're going the same distance both left to right, you can add them all in, or you can just take one side from 0 to that value and double it. Either way, if you do this and you can type that into your calculator, you get approximately 95.4%, or 2 standard deviations from the mean. So what I want to do is briefly flip back to the data that we had in the first question. In the first question, we looked at what percent lies within one standard deviation of the mean, and then within 2 standard deviations of the mean. So what we can see here is for our scores, or for my scores, my class's scores on a pre-calc quiz, 61.11 percent lied within one standard deviation of the mean. If I compare that to normally distributed data, we'd see that it's a little bit on the low side. Generally, you'd want to see more within one standard deviation. So my curve would not have enough people in this innermost location close to the mean. For a perfect curve, 95.4 are within two standard deviations from the mean. So basically this range right here. If I compare that to those scores from that pre-calc class, that's 94.44%. That's pretty close. So with my student scores that were two standard deviations of the mean, that's pretty close to being normally distributed, but we can see there was a significant difference between those that were one standard deviation. So I had probably in mine, I had a little bit more in this category here in those categories than we would prefer to see more in that category. These standard deviations, if it were coming time to take the regents, you would need to know these and be familiar with these, that one standard deviation is 68.2% from the mean, and two is 95.4% from the mean. For our class right now, for the assessment, you guys will have your notes, so you can always go back and look at these. Now, we'll continue this a little bit further. It says, how many, or also find the percentage of the population that's more than 3 standard deviations from the mean. So basically what we're looking for here in this one is we're looking for just this little end there and this little end there. And so we can see that more than 3 standard deviations, there's very little space in between that curve. And if we look at that percentages, it would be 2 times 0.1%. So this would be 0.2%. With perfectly distributed data, or normally distributed data, very few scores will ever lie outside of 3 standard deviations between the mean. Finally, question D says to find the percentage that lie between 1 standard deviation and 2 standard deviations above the mean. So notice some keywords here. This says above the mean. So what we're looking for is from 1 standard deviation to 2 standard deviations and just only above the mean. So this would be the 9.2 plus 4.4. We would not double it because we're not concerned about anything below the mean. And so this would be approximately 13.6% of scores, or percent of data, will lie within 1 standard deviation and 2 standard deviations above the mean. So these are just some representations of data and how they fit a normal curve. Now let's go a little bit further and take a look at some examples with a normal curve. So in problem number 5, it says that at Arlington High School, 424 juniors recently took the SAT exam. On the math portion of the exam, the mean score was 540 with a standard deviation of 80. If the scores on the exam were normally distributed, complete the following. A, find the percent and number of scores that fell between 500 and 600. So some information that we're going to need to use here. We are going to need to know that the mean was 540. We're going to need to know that the standard deviation was 80. Now, the lowest score that we're looking for, find the percentage. We have like a lower bound here for a lower limit that we're looking for. And we're going to eventually figure out how to do this with a calculator, but for now, let's talk about how to do this by hand. So the lowest bound that we're looking for our percentage here is 500. So let's figure out how many standard deviations we could be below the mean here. So what I'm going to do is I'm going to take this low score 500 and I'm going to subtract the mean 540. And then I'm going to divide by the standard deviations. Or the standard deviation. So what this gives me, 500 minus 540, would be the difference between the mean and my data point, 500. If I divide by 80, what that's going to do is tell me how many standard deviations I am from the mean. So if I subtract the numerator, that would be negative 40 over 80. And so this would be negative 0.5 or negative 1/2. This is, again, standard deviations above and below the mean. So if this is minus, so this would be that we are going 1/2 standard deviation below the mean. And look at how many scores are going to fall in there. So we're going to use this curve because the data is normally distributed. Now let's go ahead and do the same thing with the upper bound or above the scores. So 600 minus 540, this would be 60 over 80. Oh, sorry, that's not 600, that's 660. Here you go. So 660 minus 540 over 80, this would be 120 over 80. And if we divide this, this would be a positive 1.5, positive 3/2 or 1.5 standard deviations above the mean. So this is telling us that if we want to find the percentage and number of scores that fell between 500 and 660, we're looking half a standard deviation below and 1.5 above. So if I consult my chart, I've got a different chart up here, but it's the same chart, just not standalone. I'm going from here, negative 0.5 to here, 1.5. And so I can use my chart to go ahead and add in those percentages. I don't need to know any of the scores that were obtained. I can, if I know that they're normally distributed, I can just use these percentiles that they give us here, these percentages that they give us here, and add those together to figure out that approximately 62.4% of scores were between these numbers, 500 and 660. So that is out of the entire population, approximately 62.4% scored within that range. Now, how many total scores was that? Because we wanted to find percentage and number of scores. So if we know we have 424 juniors, we can multiply that by the 62.4%, converting that to a decimal, and figure out that we're going to have to round this number. We're going to round this down here because it's not enough to get us to 265. So 264 scores fell between or within the range of 500 and 660. So because we know that it's normally distributed data, it told us they're right there at the end, we can use this distribution curve to figure out the percentage of scores that are between these significant values 500 and 660. I don't know why 500 and 660 is significant in this case, but it is. And so we can find that 62.5% fall within that, and that's 264 of our juniors fall within that percent, within those scores. Now, we can go further. If Evan scored a 740 on her math exam, find the percent and number of students who scored better than she did. So in this case, we're just looking for people that scored better than she scored. So we know that her score was 740 here. We know that the mean was 540. So we can take the 740 minus 540, and then we can divide by the standard deviations to figure out how many standard deviations this was from the mean. So this would be 200 over 80. And if I divide 200 by 80, I'd get 2.5. So this is 2.5 standard deviations from the mean. That's where her score lied. So let me go back to this chart right here. So her score was 2.5 standard deviations from the mean. That means it was right here. This is where her score would be on the normal distribution or the bell curve. The question asked, find the percent and number of students who scored better. So what we're looking for is the percent and number of students that lie within this region. And so we can see that is very low. It's going to be 0.5% plus 0.1%. So this section right here plus that section right there. So 0.5% plus 0.1% would be approximately 0.6% of students scored better than she did. And if we want to turn that percentage into how many students that was, 740, or sorry, 424 is the total number of students that took the exam times 0.06, or sorry, 0.006, converting that 0.6 into a decimal. And so 2.54, so 2 students, because there wasn't enough to reach a third student, 2 students scored lower, or sorry, 2 students scored higher than Evan did. So she had one of the top scores in the class. And there were 2 who did a little better. So we can use this normal distribution curve to figure out information about the data or about specific points, specific student scores, people that fall within a set range, even if we don't know what all those scores or have all those scores laid out for us. Now let's go ahead and take a look at problems 6 and 7. They're going to use normal distributed data as well. So if you kind of get the concept here, go ahead and pause the video and see if you can figure out the answers for questions 6 and 7. It's going to be very similar to the concept of what we were doing there in 5, using normally distributed data on some set information. So go ahead, if you feel confident, see if you can do 6 and 7, and then play the video, and we will see if your answer was correct. So let's go ahead and take a look at problem number 6. Problem number 6 says, the heights of 16-year-old teenage boys are normally distributed with a mean of 66 inches and a standard deviation of 3. If Jabari is 72 inches tall, which of the following is closest to his height's percentile rank? So percentile means on the distribution curve where we lie, basically what's below us. So let's say we lie here, that's where our data point is. All of these percentages added together would be our percentile rank. So for Jabari, he is 72 inches tall. We know that the mean of data, or the mean of these data points, is 66 inches. So what we can do here is we can take 72 inches and subtract the mean, 66. And then we can divide by the standard deviation. Again, the reason we're dividing by the standard deviation is because this tells us how many standard deviations from the mean that Jabari is going to be. And in this instance, he's going to be 2 standard deviations from the mean. So if I go over here, this is 2 standard deviations from the mean. So basically, his percentile rank is all of these percentages added together. So what we can do is we can add up all of those percentages. Or a quicker way than doing that is this curve represents 100%. So very few people are actually taller than Jabari. So what I'm going to go ahead and do is take 1 or 100 and subtract the percentages that are taller than him. So there's only 3 of those. That makes my calculation a little bit easier. And I can see that his percentile is going to be 97.7. So he's in the 97.7 percentile for height. I can go back to the problem, and it said which one is the closest. Option number 3. So we found that he was in the 97.7 percentile, or he is taller than 97.7% of 16-year-old teenage boys. And so he is approximately the 98th percentile. 7 is similar. So it says the amount of soda in a standard can is normally distributed with a mean of 12, so there's our mean, 12 ounces, and a standard deviation of 0.6 ounces, there's our standard deviation. If 250 soda cans were pulled by a company to check volume, how many would be expected to have less than 11.1 ounces in them? So in this case, we are no longer looking at percentiles. We're looking for a number of soda cans. Concept is still the same. Let's start with 11.1 is our data point. And then we're going to subtract the mean, 12, and then divide by the standard deviation, 0.6. This is going to tell us how many standard deviations we are from the mean. And if we do that, we would get a negative 0.9 divided by 0.6, which would come out to negative 1.5. So we are negative 1.5 standard deviations from the mean. The negative tells us we are going to the left. So if I look at my chart, negative 1.5 would be right here. So we can find the percentile there by adding together the percentages. So 0.1 plus 0.5 plus 1.7 plus 4.4. So 6.7% of cans would be broken. Or sorry, not broken. In this case, have less than 11.1 ounces in them. So if we want to figure out how many total cans that is, we know that there are 250 that we are checking. So times 6.7, making that a decimal, and 16.75, or closest to 17 cans, would have less than 11.1 ounces in them. So we can use, again, a normally distributed data set in this curve if we can figure out standard deviations from the mean to predict information about data points or figure out information about data points that we don't currently have. Now let's go a little bit further. Let's talk about samples. So in problem number 8, it says biologists are studying the weights of red king crabs in the Alaskan waters. They sample 16 crabs and compiled their weights in pounds, and they're listed as followed. Now, this is not all of the crabs, obviously, that they weighed. They took a sample, and so samples allow us to determine if a population, or allow us to get an idea about an entire population, though we aren't represented with the entire population. So in part A, it says determine the mean and sample standard of standards. Sorry, sample standard deviation for this sample of crabs. So in order to calculate that, let's go ahead and use the calculator again. So hit the stat key, hit edit. I'm going to clear everything that's in there. So I'm going to go up to L1, hit the clear button, and press down, and that clears everything out. Now we want to enter in all of the data. All right, data entered. So we can use the calculator again to come up with the mean and sample standard deviation here for the sample of crabs. So we want to hit second, quit to get out of the list. Now hit stat, go over to calculate option, and select one variable statistics and hit enter. So remember, the mean is also known as x bar, and so x bar in this case is 12.59, approximately 12.59. We'll go to 2 decimals for now. The sample standard deviation here, the standard deviation is listed as 1.48, so, or 1.46 approximately. So if we knew this was the entire population, we surveyed everybody, the entire population was represented here, our standard deviation would be this value. So 1.458 would round to approximately 1.46. Let's go to 2 decimals for now. Now in part B, it says explain why this sample indicates that the normal population would be well modeled using a distribution. So what we want to do here is we want to actually use this value here. So this value S sub x that we see on the calculator. Sorry, let me back up here a little bit. So we actually, instead of, let's not write down the standard deviation here. Let's go ahead and use S sub x. S sub x is a standard deviation or a representation of deviation for a sample. And it's calculated a little bit differently here. So I'm going to go ahead and write this value down. S sub x is approximately 1.51. This value is accounting for the fact that we are not measuring the weight of every single crab here. So part B now says explain why this sample indicates that the normal population would be well modeled using a distribution. Well, what we can do here is we can take a look at standard deviations from the mean. So if I back up a couple slides, here in 4A and B, we looked at what percent of data is within one standard deviation of the mean and what percent of data is within two standard deviations of the mean. So if we want to check if this is a sample is going to be close to the normal distribution of a population, what we can do is we can figure out using the sample standard deviation what percentage of scores is going to lie or what percentage of weights is going to lie within one standard deviation of the mean. So what I would do is I would take x bar, which is the mean, minus s sub x, our sample standard deviation. And so I can do that here on the calculator. 12.59 minus 1.51. And I would come up with 11.08. And then I would also do the same thing to figure out how many standard deviations above or sample standard deviations above the mean we could go here with 1. And that would, if I added those together, I'll save you the typing on the calculator, that would be 14.1. So how many scores, if we went out and we laid out the list in ascending order, how many scores lied within these two numbers? So 11.1 is greater than 11.08, and we need to be less than 14.1. So each one of these scores lie within one standard deviation of the mean. So if we count that up, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 out of the 16 total scores are one standard deviation from the mean. If I find this percentage, this would be approximately 78.75% are one standard deviation from the mean. So either above or below. Well, let's compare that again to the data that we found, or when we looked at the table earlier, the curve earlier. We see that that is very near the 68.2% that it should be within one standard deviation of the mean. So it's not exactly perfect. No, very rarely is data perfect, but it's quite close. And if we checked two standard deviations from the mean, we could go a little bit further. If we were uncertain about these results, we could check to see what it would be two standard deviations from the and we would find a very close, again, representation there of the data. So we would say that this sample indicates that the normal population is pretty good or pretty close to a normal distribution. So in C it says, assuming your mean and standard deviation from part A apply to a normally distributed population of crabs caught in Alaska, what percent will fall between 9.6 pounds and 15.6 pounds? So go ahead and pause the video here. This is similar to some problems that we've done. Go ahead and pause the video and see if you can figure out the answer to part C. Okay, hopefully you've had a chance to come up with an answer. So what we want to do here is we have two data points that we're trying to find the percentage between. So we have some data points that are below the mean, and we have some data points that are going to be above the mean. So let's start with below the mean. 9.6 is our lower bound. And so I'm going to take this 9.6 minus our mean, which was 12.59, and then divide by now the actual standard deviation. Or sorry, our sampled standard deviation here. So our sampled standard deviation is this value 1.51. So I'm going to go ahead and divide by 1.51. And as I do that, I'm going to come up with that I am two standard deviations, or approximately two standard deviations below the mean. So again, we could do this all in the calculator. So 9.6 minus 12.59 divided by 1.51. And we'd see that this is roughly 2. Again, I've been rounding some numbers, and so that's why that's not quite on, but approximately 2 standard deviations from the mean. We do the same thing for values that are above. So for above, we'd have 15.6 minus 12.59 and divide by 1.51. And we would get approximately 2 standard deviations above the mean. So going back to my normal curve, I'm 2 standard deviations below the mean and 2 standard deviations above the mean. So I'm going from here to here in between those two values, and you could find those percentages, add them together, or if we do remember from earlier, 2 standard deviations from the mean would be approximately 95.4% of these crabs will fall within that range. So in this process, we are actually using what is called a z-score. So as we've been going through here and we've been trying to find these values or these percentages, we've been using a process called z-scoring or finding a z-score. So what a z-score is basically assigning a number or quantifying the score, the distance from a data point to the mean in terms of the standard deviation. And so how we find that z-score, and we just did this, but let me go ahead and represent this with a formula. To find the z-score, we take any data point, so let's call it x sub I as the data point. We subtract the mean, let's call that x bar. That can also be mu, but we'll just use x bar, and divide by the standard deviation. So the only new thing here is that x sub I is any data point that we may be using. So this z-score is what we've been finding, how many standard deviations we are above and below the mean. So in problem number 9, it says, boys' heights in the 7th grade are normally distributed with a mean height of 62 inches and a standard deviation of 3.2 inches. Find z-scores rounded to the nearest hundredth for each of the following heights. Show the calculation that leads to your answer. So for 66, if we have a data point that is 66, we want to find that z-score. We're going to take 66, this data point, minus the mean of 62 divided by the standard deviation of 3.2. And we can do all of that work in the calculator. So 66 minus 62 would be 4 divided by 3.2. So the z-score here would be 1.25. So a positive z-score means we are above the mean. A negative z-score means we are below the mean. That's basically what we did on the last couple problems. So see if you can pause the video and find the z-scores for both B and C, and then play the video when you have found the answers. Hopefully you've gotten a chance to come up with answers for B and C, finding the z-scores. So again, we're taking the individual data point and we're subtracting by the mean and then dividing by the standard deviation. And so it gave us the mean and the standard deviation in the problem for 9. So we can substitute in those values, and so we'll approximate that if we need to, rounding to the nearest hundredth. And we'll see that the z-score for B is negative 1.56. So the data point is 1.56 standard deviations to the left of the mean. For C, 70 minus 62 over 3.2. So the data point divided by the mean, minus the mean divided by the standard deviation. And we get about 2.5 or 2.50. So we are 2.5 standard deviations above the mean. Now, what we'll notice is that some of these land perfectly on one of our lines for standard deviation, 2.5, 2, 1. Some of them do not. So 1.25 and negative 1.56 are going to lie within some points. So 1.25 would be somewhere in there. Negative 1.56 would be just next to that line, somewhere in there. So when they land exactly on one of our standard deviation lines, coming up with percentages is a fairly short and easy process. When they don't, we have to go through some additional steps, which we'll see here in a little bit. Let's go ahead and take a look at another problem. Problem 10. Jeremiah, who took a standardized test score where the mean was 560 and the standard deviation was 45. If Jeremiah's score resulted in a z-value of 1.84, then what was Jeremiah's score to the nearest whole number? So again, we have the z-score formula. Z-score is the data point minus the mean divided by the standard deviation. So here in this case, we actually know what the z-score is, so we can substitute in that z-score. That z-score is 1.84. We don't know what the data point is, so x sub I, I'm going to leave it there. Minus, we do know the mean, it was listed as 560, divided by the standard deviation, which was 45. So now what we want to do is we want to solve here for x sub I. So we want to get rid of the fraction. To get rid of the fraction, we would multiply both sides by the denominator. Let's multiply both sides by 45. So 82.8 is going to be equal to that data point minus 560. Now I can add both sides, or sorry, 560 to both sides. And so I would get that 64.8. We want to round to the nearest whole number to get a score here. His score was a full number. So 643 is Jeremiah's score. So we can use that z-score formula to tell how far things are away from the mean in a value of standard deviations, or if we know the z-score, we can use that to come up with specific points along the curve. Now, let's take a look at problem number 7. And this is in instances where we're going to have values that don't exactly fall right on a standard deviation from the mean. So, or a set one that falls on that curve. So if, again, like the z value of 1.84 on that curve, 1.84 is going to end up somewhere over here. So we wouldn't be able to use percentages to find that score if we needed to. What we can do is we can use the calculator and created an idea of upper and lower bounds. So what we saw, let me scroll back a little bit. What we saw right here in problem C, talking about the Alaskan or the red king crabs in Alaska, we wanted to find the percentage that lied within two set boundaries. And we were able to do that because we found that it was exactly two standard deviations above and below the mean. And so we can add up those percentages, etc. Now, if we're somewhere in between, we can't do that. But what we can do is we can use the calculator. The calculator can give us that information. So in problem 11, it says, given that the volume of soda in a 12-ounce bottle from a factory varies normally with a mean of 12.2 ounces and a standard deviation of 0.6 ounces, use your calculator to determine the probability that a bottle chosen would have a volume of each of the following. So we want to figure out what's the probability that the volume is going to be greater than 13 ounces. So again, if I wanted to attack this using z-scores, I could look here and find out that the z-score for this would be taking that 13 ounces minus 12.2 and dividing by the standard deviation. So that z-score would be 0.8 divided by 0.6, which would be 1.3 repeating. Again, 1.3 repeating does not show up here on our graphical representation of the normal distribution curve. So I can't figure out the percentage, therefore I can't figure out the bottles like I did previous. What I can do is I can use the graphing calculator. So if you have the graphing calculator, we can come up with a z-score if we wanted to, but we don't really need to use it. What we're going to do instead is we're going to kind of get an idea of what it is that we're looking for here. So I'm going to draw a graphical representation. Here's my mean. It's 12.2. And here's a rough sketch of the normal distribution curve. And here is 13 ounces. So just randomly put 13 ounces on there. What I'm looking for is what's going to fall in that shaded region. That's all I'm really concerned with. What percentage is going to fall in that shaded region above 13? So how I can do that is using a function on the calculator. This function is the normal CDF key. So to find that, we hit second, and then we hit this vars button here, variable statistics button. The second option here is normal CDF. Now, on newer calculators, when you hit that, you're going to come up with a menu presented to you, likely. The first thing it's going to ask is for the lower bound. So basically what we want is the leftmost value of the shaded region. And so we're going to type in 13. Now in the newer calculators, you can type in 13 and then hit enter. On the older calculators like this, you want to type in 13 and then make a comma because it's going to be a different representation. The second number that we want to put in is the upper bound. Now, in this specific problem, we don't really have an upper bound. So we kind of want to choose a drastic number. So maybe 1,000 ounces. The upper bound, this curve is going to go to the right for infinity. It's going to go on forever. So we want a big number, 1,000, maybe 10,000, maybe a million. A rather large number that's going to stretch that curve out very far to the right to where numbers are no longer going to be recognizable. So in the older calculators, you're going to type in that upper bound. I use 10,000. So with the newer calculators, you want to type in 10,000 by upper. Where it says mu in these older calculators, mu, remember I just spoke on just a minute ago, mu is the same as mean. Mu and x bar are the same thing. So mu just means mean. And so that's going to be the third value we type in. So if you're on an older calculator, put a comma and then type in that value, the mean, which is 12.2. On the newer calculators, make sure you type in 12.2 at that location. Then the last thing that we're going to type in is the standard deviation. And so you should see that symbol on the newer calculators, lowercase sigma. So you can type in 0.6 on the newer calculators. On older calculators, we're going to put in comma and then 0.6. And then hit enter or paste on the older calculators. So what you'll see is this on the newer calculators. What you'll see is this written out as well. So let me walk you through that again. What we have here is we're going to have normal CDF. We're going to have our upper bound, our lower bound, then a comma, then the upper bound, then a comma, then x bar or mu, which is the mean, and then this comma, then standard deviation, and then close your parentheses. And so the newer calculators do that for you automatically. The older ones, you have to type that in. And now we get the percentage or the probability. So what we get here is that 9.12, approximately 9.12% of the soda bottles will have have a volume that is greater than 13 ounces. So this is, again, basically what we did over here in problem 5, where we found that standard deviations to the lower bound, and we found the standard deviations to the upper bound, and then we used the curve to figure out percentage, and then percentage to figure out scores. Basically what we're doing is all of this work here on the calculator. So let's go ahead and take a look at another example. In example B, it says we want to figure out how many are going to have a volume of less than 11 ounces. So again, if I want to draw this out as a graphical representation, I'm no longer going to use the z-score here. I'm just going to use my calculator because it does tell us to do so in the directions. And so if I have kind of a normal curve here, rough sketch, doesn't look good, but that's okay. I'm using less than, or looking for less than 11 ounces. So here's my bound, and I'm looking for the left here. So I'm going to grab the calculator. I'm going to start by hitting second, variable statistics, down to number 2, normal CDF. The first number we're going to type in is the lower bound. The lower bound in this case, so we would be going to the left forever, or in instance of this problem, the lower bound is just going to be 0. So once I hit 0, that's the least amount of ounces that I can have. So my lower bound would be 0. So the furthest to the left on this curve. Then the upper bound is 11. That's the furthest to the right on the curve that we're looking for. Then I'm going to put another comma. I want to have my mean, which is 12.2. I'm going to put another comma. And then I want my standard deviation, which is 0.6. I'm going to close those parentheses, and then this is going to give me the percent. So approximately 2.28% are going to have less than 11 ounces. So again, this is a faster way. This is a way of using a normal distribution curve, but it's a little bit faster than going back and figuring out those percentages by hand. See if you can pause the video at this point and do C. Find out the percentage of soda bottles that are going to have between 11.5 and 12.5 ounces. All right, hopefully you got a chance there. Go ahead and find the percentage. So I'm just drawing out a sketch here, a rough sketch again of the normal distribution curve. So in this time I'm going from 11.5 to 12.5. So 11.5 is a lot further from the mean than 12.5 is. So we're going to have a little bit or more data points to the left of the mean than we are to the right. But the calculator will still record that or calculate that for you. So I'm going to hit second, variable statistics, the second option, normal CDF. My lower bound this time is 11.5. The lowest I'm going is to the furthest to the left is 11.5. The upper bound is 12.5. My mean is my third value that I'm putting in, which is 12.2. And my standard deviation is my fourth value, 0.6. And close those parentheses. So here we don't have to worry about percentages. We don't have to worry about how many standard deviations that we are from the mean. We can just take those given data points that they give us and go ahead and type that in and calculate. And we get here that approximately 56.98% of the soda bottles are going to have between 11.5 and 12.5 ounces in them. So this is a way to establish a population portion using normally distributed data and the calculator to come up with those percentages. Finally, the last thing that we're going to talk about is distribution of sample proportions. And so in interest of time and the days that we have here due to our current situation, I cut out a lot about sample proportions and samples. Basically what we have here when we talk about sample proportions is basically if you think about having a group of people. So here I've got a group of people over here and I want to do a survey. It's not going to be possible for me to do a survey of all people. Say there's too many, I don't have enough resources. So I'm going to choose a sample. So here I choose these 6 people and I survey them to represent the whole group. Or maybe I could do these 6 people. I would, in that case, I could represent or sample 2 different groups of 6 people and get different results. Both of them, though, would ideally represent the population. Slightly different results would ideally represent the population. The bigger my sample is, the better results I'm going to have. So if I sample 9 out of that entire population, it's going to be better. If I sample 15 out of my total 25 here, it's going to be even better. So when we talk about samples, we can run simulations to create sample representations of data from surveys of or drawing from smaller groups of a population. So that's kind of what we looked at, a little bit of what we looked at in problem in the previous problem with the Alaskan crabs. Now, what we're going to find here is we want some things to be true. So if our data is going to be good and accurate, there's going to be 3 things that we look at that need to be. So the first thing that we want to be true is we want the data to be approximately a normal distribution. So depending on how many samples we run or how many samples we take, how many simulations we run, eventually we want to gather enough information for the data to be approximately a normal distribution. Maybe not exactly, but the closer the better. The second thing that we're going to have is a mean population portion, which we call P. So the average portion of the population is going to be P. It's going to be a set number. The third thing that we're going to have, and this is going to be kind of a little bit of an ugly formula here, is we want what we call P hat to be, the standard deviation of P hat to fit a formula where we take the square root of P times 1 minus P divided by N. And we could talk about why this formula is the way that it is, but we'll save that for statistics. So this is where N is the number of data points in a sample. So we want, if we're going to take a sample of a population and we're going to run simulations, and we skip the whole running simulations, but basically we're going to take a sample and we're going to predict values over and over again. We're going to run simulations. We want these three things to be true. So if I go ahead and take a look at problem number 12 says a simulation of samples taken from a population with a proportion of 0.3, so that's our p-value, was created. The simulation had a sample size of 100 and 500 simulations were run. So we had a population, we took 100 samples out of that population, we ran 500 simulations. The sample proportions p hat. So the sample proportions, this is the proportions of our sample, not the exact population. The population proportion was 0.3. The sample proportion, this is what we call p hat, meaning that it's from our sample, were calculated and their distribution is shown below. So basically we ran a group of simulations, and this is the proportion that we came up with. So if I looked here, the proportion of this group by itself, which we call p hat, would be 0.2. If I looked at this proportion right here, p hat would be 0.4. So those values weren't exactly what we had from the entire population. But if I go ahead and look at the multitude or the combination of all the simulations that are being run, I can see the first thing here is that this curve is normally distributed. We're pretty close. So I drew in a sketch to represent the curve, and that data is pretty close to a normal distribution. It's not exactly perfect, but it's close. So I hit the first thing that I want here for a sample population. The second thing is I want the mean population portion P to be the same as P hat. So P hat, again, is the mean of that population proportion we can see here. So if I took the mean or the average of all these little data points in there, there's 100 of them, it's 0.0301. So P hat and P 0.3 are approximately the same thing. So P hat is approximately P here. This is good. The other thing that we see here is that the standard deviation of P hat is this number. So running all of these simulations and gathering all these data points, you can use your calculator to come up with the standard deviation that was already given here for us. And I didn't want to make you guys learn how to do all that work, so I gave it to you. The standard deviations of P hat is given right here. What we need that to be is to represent that formula that we saw on the last page. So we need the standard deviations of P hat to also be P times 1 minus P over N. And so P, in our case, is the population proportion, which was given to us as 0.3, times 1 minus P, which would be 1 minus 0.3, so 0.7, over N. Remember, N is the number of data points that were taken. So there was 500 simulations, but that was from the sample size of 100. So this value 100 is equal to N. So if I go ahead and input this into my calculator, I'm going to take the square root of 0.3 times 0.7, and then I'm going to divide that. I need another set of parentheses here. Hold on. Make sure we get the correct input method here, and to make sure that we have our 100 inside the square root. Here we go. What I get is approximately 0.046. And so this value, standard deviations of P hat, is very near this formula, the square root of P times 1 minus the quantity 1 minus P divided by N. So we have a sample or enough simulations here that the sample data that we're drawing from is representative of the population. Okay, so Again, I'm not going to make you come up with this information. All this information would be given to you. Let's take a look at an example problem of how this is used. So in problem 13, it says, suppose the percent of seniors in high school that own a cell phone is 82. If a random sample of 50 high school seniors was taken, determine the following. So A, the standard deviation of sample proportions for this population or portion given the sample size. So if I want the standard deviation of sample proportions, that again is finding the standard deviation of p hat. Sorry, let me write the correct notation in there. Standard deviation of p hat. So that was that formula that we just got. P times 1 minus p divided by n. So p is the population proportion here. And so the population proportion is that the percent of the seniors that own a cell phone is 82%. That means that's our population proportion. 82% or 0.82 of the seniors have a cell phone. So then in parentheses, we take 1 minus p, so 1 minus 0.82. And then we divide that value by the number of students that were sampled, 50. So it's a high school, large high school. We sampled 50 instead of all of them. So the standard deviation for our portion of the population that we took is going to be this quantity. So we're going to take the square root of 0.82 times 1 minus 0.82 divided by 50. And so this is going to be approximately, the standard deviation is approximately 0.0543, or approximately 5.43% is our standard deviation. So it says in B that we want to determine the probability that the sample portion will be within 3% of the 82% proportion, and we want to illustrate our work here. So what we have here is basically what we're looking at is our mean of our samples needs to be 82%. So our population proportion should be the mean, which is 82%. 3% from that would be 85% above and 79% below. We want to figure out the probability that if we take a sample of 50 students, that our mean or our results is going to say that between 79 and 85% of our seniors own a cell phone. So if we do that here, we can do this using the normal CDF button. So this would be the curve we're looking for, what's going to lie in between 79 and 85%. So I would hit second, variable statistics, normal CDF. My lower bound is first, 0.79. I hit a comma and then put in my upper bound, that's second, 0.85. We're putting those into decimals for the computation. Then I want the mean, which is 0.82. And then finally, I want the standard deviation, which we just did was 0.0543. So what we come up with here is if we sample 50 students, there's a 41.94% chance that we are going to get our sample to say that between 79 and 85% of our high school seniors have a cell phone. So this is kind of a low percentage. So we may want to realize that, hey, we may take a look at this and want our data to be a little bit more accurate. So maybe we need to sample more people. In C, it says find the probability that the sample proportion will be less than 75%. So here again, I'm going to sketch out an illustration here. 82% is the mean of the data, or what we want to be the mean of the data. That was our population proportion. And we want to figure out how many are going to be less than 75%. So 7 percentage points away from what the actual data should be representing. So if we want to do this in the calculator again, so second, variable statistics, normal CDF, we're going to have our lower bound. In this case, we're to the left of 75, so our lower bound is 0, all the way down to 0%. 0.75 is our upper bound. Our mean is still 0.82, and our standard deviation is still 0.0543 for p hat. So then we can evaluate that, and we can come up with the probability is approximately 9.87% chance that our survey, our sample of 50 seniors, our survey is going to say that it's 75% or less of our seniors have cell phones. So go ahead and see if you can do D. Find the probability that our sample is going to say that greater than 95% of our seniors have cell phones. So pause the video now and then check back to see if you got the right answer. Okay, so hopefully you have an answer. Here I am drawing up the curve. Again, it's just an illustration, so it doesn't have to be exactly perfect. So we want to know what percent is going to be, or what's the chance, basically, what is the probability that our sample of 50 seniors is going to show that we have over 95% of the seniors have a cell phone. So I'm going to hit second and then variable statistics, go to normal CDF. My lower bound here is 0.95. My upper bound, you could exaggerate that number, put in a large number, or we could just do 1 because we know that this goes up to 100%. So that would be the highest value that we could possibly have in this case. If you put in a number like 10,000, that would be okay. We want to make sure that we get in the appropriate mean number, 0.82, and standard deviation for our sample, 0.0543, and then calculate the percentage. And we come up here that if we sample 50 seniors from our senior class, approximately we have an approximate chance of 0.79% of having a result that says 95% of our seniors have cell phones. So this is basically us coming up with some efficacy to our sample size. Is our sample going to be a good representation of actual data? And we'll see a realistic example like this. This one is actually recently, not super recently, but fairly recently applicable. Problem number 14, it says 47% of the public will vote for a particular candidate in the upcoming election. This is the known population portion. It says if a newspaper takes a random poll of 200 voters, what is the probability that this sample will have a proportion larger than 50%, thus predicting a candidate that is going to lose to actually win? So again, it's an upcoming election, so they're not polling everybody. They're just going to poll 200 voters. And so the first thing that we're going to need to do is we're going to need to find the standard deviation here for this sample of the population or population proportion here. So the standard deviation for p hat. So our population portion that we know to be true is 47% of the public will vote in favor of the candidate. So that is our p value here. This is p, not p hat, just p. So 0.47, and then in parentheses we'd have 1 minus 0.47. And then we would divide by n, which is the number of people that we are polling. Here would be 200. So if I want to find the standard deviation for my population portion, my sample, I'm going to have 0.47 times 1 minus 0.47 divided by 200. So my standard deviation here is 0.353 approximately. So this would be, if we're because we're talking about percentages of voters, this would be approximately 3.5% of voters. So what is the probability that if we poll 200 people, it's going to tell us that a candidate that, again, is going to lose actually wins? So what I would do here is my population portion, P.47, is my mean on my normal curve here. And I'm looking for what's the chance that I'm going to get greater than 50 people say they would support, or greater than 50% say they would support the candidate. So, second, variable statistics, normal CDF. My lower bound is 0.5. My upper bound would be going to the right of 0.5, so on forever to 1. My mean here is 0.47, the population portion for the full population. And then my standard deviation is 0.0353. So if I find this value, I would have approximately a 19.77% chance that my sample would actually predict the wrong candidate from winning. This actually happened frequently when you look back to the last presidential election. Almost every sample that was taken had Hillary Clinton winning the election. But when they actually hit um, the time for the election, you guys know, Donald Trump ended up winning that election. So here, they may have found this, these aren't exact data, but they may have needed to survey more voters or run greater samples so that they would have a less chance of being inaccurate with their sample. Okay, so this is just a brief overview of population proportions. Actually, in reality, we're not going to do a lot with population proportions. I just wanted to make sure that we touched on it a little bit before you guys got to statistics for those of you that are going to go in that direction. The focus of this is being able to understand the normal distribution curve and being able to apply information based on this curve, whether you have the curve and exact standard deviations from the means to the nearest half standard deviation, or whether we have examples where they are part of a standard deviation from the mean. We have a z-score that is a fraction or a decimal or an irrational number, still being able to find percentages of populations that meet certain conditions. Okay, so at this point, guys, we are finished with PS3 notes. This is the last notes section that we will have, so you guys are done taking notes for Algebra 2 this year. The homework is posted or will be posted very shortly. You can go ahead and get started in working on that homework. Our online assessment over PS3 is to be coming on June 2nd. That's a Tuesday. Take a look at Google Classroom. Make sure that you guys have information regarding the end of the year, extra credit, all of those other key information pieces will be posted on Google Classroom. If you run into questions before our next Zoom session, reach out to me via email and I will see what I can do to help you out. Thank you guys for tuning in. Have a great day.